So hello everyone, I am going to go through the FPGA flow regarding the, the lab that we did the last Thursday. I will not do it for the whole top module. I will just do it for this architecture. Here you can find the generate reset block and the two counters and the multiplier. And I will use SignalTap so I can detect the result of the multiplier block. As you can see, the enable and reset signal are the input for the two counters, and the same clock enters the two counters, and the two counters count from 0 to 15. This is because of the width of the count, it is 3 to 0, and both counters give the same input. Actually, we can use one counter and put it as input A and the input B. However, this is for simplicity. So the multiplier now will do something like power 2. So 0 power 2 it will be 0, 1 power 2 it will be 1, 2 to the power 2 it will be 4, 3 to the power 2 it will be 9, and so on till 15 power 2. The code, the VHDL code is compiled and it is correct, but I will just go through the new project wizard. This asks for the path of your design. I put my design in the desktop. So lab 1 video, select folder. Usually it is better to put the name of the top module as the name of the project. Here is my top module. Next, empty project. We can now add the files. Next, here we are going to specify what is the board that we are using for the FPGA. For us it is 5CEBA4F 237. This is the one. So next, for simulation part we usually do model sim altera, but actually we are not going through this step. So next, you should specify the format to VHDL and finish. After getting the hierarchy, we need to see the files, so we can see the whole files we will put beside the VHDL files. We will add an STP file, this is for the SignalTap, and the SDC file, this is for the clock. In order to make sure everything is right, we need to put the top module as the top entity level. Now we'll just use compilation. Usually a common mistake, it is just by doing compile design. So compile design will go through the whole flow, and this might give you an error while doing pen assignment. So you should do it carefully and step by step. So first, analysis and elaboration. This will compile the whole HDL blocks. As you can see in the taskbar, it is just loading, and here are the messages. These are the warnings and these are the errors. So HDL, this is the warnings, all. Okay, now it is green check, so everything is okay. We'll just do the assignment. We'll go to the pen planner. Before going to the pen planner, you should see the assignment editor. The assignment editor here is just blank, no assignment, just wait. If you made the common error and do the compile design, you will see the whole input output or the preference already assigned here. So when you come to the pin planner and put the location for your input, he will just give you an error message. So you need to come to the assignment editor and remove the location or the pin that got the location that you want to reserve for your signal. So as long as the assignment editor is blank, now we can return to the pin planner and just to put the location for our inputs. This is the location. You can see this red box. It is just for the clock. It means that for the M9, now we reserve this for the clock. Okay, M9, 9 from below. Okay. The thing is, the location you can just get it from the manual of the FPGA board. In the FPGA board, this is the FPGA board that you are doing. Yes. As you can see, there are 7 segments, and there are 10 switches, 4 buttons, and for every one of these 7 segments there is a location for each pin. So actually what the pin assignment does is just assign the input in your design to this location, and the compiler or the Quartus will just know that this clock is already assigned to the clock that we use. I will get to the clock. Here is the FPGA clock. It is named clock _50, and its location is pin _M9. So my clock that was CLK clock just will be assigned to this pin. So the compiler will know that clock 50 is already my clock. This is the importance of the pin assignment. Also, for the result output, I will just put the result. I will assign the output of my multiplier to these slits. So I will just go these slits and assign it in the pin planner. Let's come to the pin planner. For result of 7, it is pin _EA2, pin _EE1, sorry, pin _EE2, pin _EE1, this is just not compatible with what I put in the table, so I'll just remove it. So again, this is pin EE2, pin EE1, this is pin W2, this is pin Y3. As you can see, as long as I go through the pin assignment and location, you can find the location is already in a red circle or a red box. Pin N2, pin N1, pin U2, pin U1. Now I just finished the pin assignment. I will just export the pin location in .csv file. Now the Quartus tool, know that I made a pin assignment for this. You can find in the assignment editor that this clock is just assignment in the location of pin M9 and so on. Now return to the flow. We will just do until we finish until we get to the timing analysis. Now we compile the design. We made the pin assignment step, and now we will just create our clock as specified in the manual. For creating the clock, we will just need to add another file that is called a .sdc file. It is called synopsis design constraint, and SDC is the shortening of the name. So in the .sdc file, you can define the uncertainty, you can define certain or other constraint on the paths, but since our design is just simple, we are not going through many details in the .sdc file. We just create the clock and tell the compiler that our clock is the signal CLK clock. We can do this by the timing analyzer. It can't be open while compiling, so we just need to wait for the compiler to settle. Okay, now we are going to the timing analyzer. You will need this whole step and the generate reset for the rest of the labs, I think. So you need to so this whole step will just be a repeated process for you. So this is the window for the timing analyzer. There are, as you can see, a lot of reports and a lot of checks. We will just create an SDC file. In this SDC file, we will just define two lines, or define two commands. These commands set time format. That means that the unit of the time is by nanosecond, and we use 3 decimal places. So when I create clock by this command create clock, it asks about its name and its period, of course. So file, save as sdc1.sdc. After saving the file, close the timing analyzer. You can find that the SDC file is already added to your files in the project navigator window. Doing so, we can do the timing analyzer and the EDA netlist viewer. So we can, in the timing analyzer, it will just do the timing. It will assign see the clock is clock, and its frequency is 50 megahertz. So EDA netlist writer, it will just write the netlist or do the simulation using the model sim Altera that we specified in the first of the project, but it is not our topic now. So now we are ready to complete the whole flow. After completion of the whole flow, we will just go and program the device. The program of the device, it is used by G-tag. It will just insert our file that the Quartus made, that contains all the information about the pin assignment, about the clock, about the logic and the memory elements, and program the FPGA. You can know what kind of FPGA that is connected to your PC by just select on the auto detect, of course. And this in hardware setup, you can see there are two FPGAs connected to the PC, but for the undergrad it is USB cluster, of course. And this is the name of the device that we are using to compile. and after the compilation is done successfully, we can just click on the start, so the whole project is loaded to the FPGA. After this step, we will go to the SignalTap analyzer and add a new file that has the extension .stp, and we will just go through the whole information about it. Now we'll just go to the and click on start. Now you can see the progress bar, it is successful, so our project is loaded for the FPGA. So now currently the FPGA is working on our project. Anyway, we will just go to file, new, SignalTap to logic analyzer. Currently what you are seeing is that our program runs successfully, and now it is on the FPGA, but you can't see the result. So what are the proper method to see the result is by using SignalTap logic analyzer. SignalTap logic analyzer is just as it works as an oscilloscope in order to specify the whole objective of SignalTap. You can probe any signal in your design and specify certain memory elements inside the FPGA, so it can collect or capture data when certain events happen. So in this SignalTap window, you can see that the USB cluster, it is our FPGA, it is already here, and the device, so everything is connected to our FPGA. For the signal configuration, this clock, you can just select any signal in your design, but it is preferable to use a non-gated synchronous signal. In our case, it is a clock, so we will just enter clock. Sample depth, it is the amount of memory elements that will be allocated for you on the FPGA in order to capture the data. And this is the triggering condition. We will use two trigger conditions. The trigger condition, it is the event that when it happens, the FPGA will start to capture data for certain nodes. What are these nodes? These nodes that you can specify just by double clicking here in this white area. We need to just increase the size of this window and list, do pre-synthesis and just to collect on list. You can see the whole signals that we put inside the VHDL code. You cannot put the clock in the nodes found because we use the clock to sample the data, so we cannot use the clock to capture its value, so it is inappropriate. And for the result here, we need to add the 7, the 8th pins, and for the generate reset, you can just add the enable and reset in order to see that when the enable and reset are put, our design starts to work. So insert, then close. Basic AND and basic OR operation, you can just put here on the result 0, you can put if it is don't care, so I just interested in its information. So if it will be low logic value 0, or it will be falling edge, rising edge, or high logic value 1, or either edge. I will just use this to be when enable is 1, and this when enable is when reset is 0, and specify that for the multiplier output when either edge starts to change. Actually, I am connecting through VNC, so the whole process might be a little bit slower than usual, so excuse me for this. And we can do for this basic OR and this basic OR. This is when the whole conditions are ORed with each other, so it is my trigger condition, and this is for these two conditions to be ORed with each other. Now after doing the SignalTap, we just need to save the file. It will be saved in the project path in the output files, and click on save. Yes, we would like to save this, and before going to see the signal, we just need to recompile the whole design, because now the .stp file is just added to the new file, and it will, and we asked the Quartus to add certain or allocate this amount of memory. So the whole file that we will use for programming the FPGA needs to account for the logic for these trigger conditions and for the space and memory to capture the data. So whenever you do any change to the nets, increasing the nets or decreasing the nets, or increase the depth or decrease the depth or increase the trigger condition, you need just to recompile your design. And there are two compilation scenarios. The one is the usual compilation, and the other is the rapid recompile. So rapid, it will be just faster. We'll use the rapid. After finishing the rapid compilation, we will just need to go to the program device and program the FPGA once again. Now just leave it 2 minutes to finish the compilation. Doing so, we can elaborate much more on the trigger condition here. In the trigger condition, there are many conditions, and there is an advanced conditions. You can see in the documents, SignalTap with logic analyzer in Altera with VHDL. There is advanced option that you can see. You can enter many signals, and you can just specify different condition, either falling edge ANDed with each other, and then two signals ORed with each other, and the output of both two ANDed with each other. So it will be your trigger condition. So the trigger condition is not, it can be much complex as you want, and the Quartus will do this for you. For more information, I advise you to go to the manual and read more about the triggering condition using Quartus. So let's just wait for the compilation to finish and program the design and see the data. So now with the programming of the device, you can see here is the device. Now we are clicking on the start. Update the file. Still it didn't finish. So program progress. Now it is successful. So in order to see the SignalTap invalid GTAG configuration, don't worry, just click on the run analysis. Now acquisition in process. Now here is the data. It is it is not like the test bench that you use on model sim, because actually this is a real logic values from the FPGA. So it captures inside the memory these data, and it returns to you the logic values of each one. So remember from the design, our design was like this. So the two counters usually output always outputs the same output, so 0 0 1 1 2 2. So as you can see here, the result here is 1 before result is 1, result here is 0, and result 1 is 0, and the whole results are zeros. So this is 0 for second thing, this is 1, and 2 times 2 it is 4, so this is 4, it is result 2, and this is 0 0 and the whole 4. And you can go through till you can find that this is 15 times 15, result 7, result 6, result 5, the all are 1, and result 0 it is 1, and the rest are zeros. Interestingly, that result 1 is always 0 doing this multiplication. I hope that you benefited from this video. Please let me know if you have any inquiries or something that didn't go well with you. Thank you.